Okay, ladies and gentlemen, I think we left off around heat transfer, basically. We're talking about multi-phase, and we were talking about primarily heat transfer. We were saying last time that three phases, usually the third and fourth phase, usually reduce transport. Sometimes multi-interactions can be significant. Anyway, let's go on to heat transfer a bit. Heat transfer. Now, process objectives. Let's try my slides, I guess. Slideshow from current slide. And we get some pointer options up here. Highlighter, and first we get ink color, and then we'll get highlighter, hopefully highlighter. Okay, I lost my ink color. Jeez, oh man. With such a sophisticated thing as PowerPoint, you would think that they would have good online graphics, but I guess they're not anticipating. It'd be generation 2 or 3, huh? Anyway, heat transfer. Process objectives are varied, quite a few. You're either heating, cooking, coking, melting, freezing, cooling, crystallization. Many processes are heat transfer process or heat transfer control processes. Quality and proper operation are closely related to heat transfer. Heat transfer, you want a good liquid fluid circulation. Good exchange at the surface. You want to try to avoid hot spots or cold spots, and you want to try to prevent the loss of product quality and loss of product. Heat transfer becomes important in larger processes and may control the size of the process. Cooking may require large amounts of heat, for example. We also find that jackets are not very effective on volume processes, i.e., as you scale up, the heat transfer jackets become less important. On the internet, I was observing how you do a scale up of an exothermic reaction, and small scale, test tube or beaker size or maybe even liter size, everything was fine. Temperature excursions or the temperature rise from the exothermic reaction was controllable. But the chap then proceeded to do a scale up to maybe a 5-gallon or 100-gallon vessel, and his temperature reached 1200, 1800 Fahrenheit. Obviously, that's not a very effective scale up. I'm quite sure that something bad would have happened. So obviously, as an example, small scale can be controlled quite well, or reasonably well. Large scale with large heat releases become quite another matter. Massive internals are added on large scale to obtain the necessary heat transfer area. Nuclear storage tanks for nuclear waste storage tanks have massive internals in there for taking the heat out. Basically, massive internals are not needed small scale. There is a large surface area to volume ratio on small scale. It disappears on the large scale. On scale up, problems occur. Circulation patterns are altered. Dead zones form. You have a lower heat transfer coefficient. In fact, the prediction of the heat transfer coefficient becomes difficult. You're probably going to have to measure it or use data. You have an increase in fouling, and the calculation of an effective Reynolds number becomes very difficult. In one reactor I ran into, it was very symmetric. Basically, as I recall, it was sort of like this. And for some reason, it fouled only on one side, basically. I think the feed stream came on this side and never really effectively went over here. Only in the bulk did it go over. And it was really strange that the fouling occurred on one side of the reactor and not on the other. Anyway, design should not hinder liquid circulation. That's real difficult when you're trying to put in the heat transfer surface and you're trying to get the heat out. You often block off the liquid circulation. Process Reynolds number is less significant. Small scale equipment use the same heat transfer geometry as the large scale. This allows for the appreciation of heat transfer problem. I mean, on the large scale, if you're going to use massive internals, then you should try seeing what effect those have on the small scale. Another phase always complicates things. Gas will lower the heat transfer coefficient, affect the liquid circulation. Bubbles can attach to the area, heat transfer area, and gas pockets may form over the heat area. You can have what they call vapor lock, where basically it's heated so much that you've boiled the liquid and there's a vapor lock around the heating element or around the element that's taking out the heat. That's a different story. So we have this very famous equation. I picked this up when I was an undergraduate student by George Klinzik at the University of Pittsburgh. Very, very nice, honorable person. Laminar flow plus heat transfer equals many problems. Laminar flow usually causes poor liquid circulation. Materials may burn on the surfaces and the heating elements may actually overheat. Now what's really interesting is the reverse. The heat transfer coefficients can easily be measured and calculated, right? You can go out and measure the temperatures, and you can go out and measure the flow rates, and you can back out the transfer coefficient. And it can be used as a diagnostic tool. Obviously, it will tell you perhaps when to clean, right? When to clean. Let's go over here. So what happens is you have the heat transfer coefficient, or say overall heat transfer coefficient. That's the U times the area. And down here you have time, basically. And what you can do is, over time, denote the drop in the heat transfer coefficient over time. At some point, the performance becomes unacceptable, right? And you decide that. So then you go down and clean, okay? And the cleaning is going to take a little bit of time. And suddenly you're boosted up here, and then you come back down, and then you do some cleaning again. I guess you got to go way down here. Anyway, so the increase in performance that you got due to cleaning is this area in here. The cost of the cleaning was this area in here, the downtime basically. This is an improvement in performance. So the question becomes, is you take this area here and divide by this area and plot that versus cleaning time or cleaning duration. And so you have perhaps an optimum point where this would be the optimum. Obviously, you want to maximize this and minimize this. So you have that ratio, so we'll call that ratio R, and you plot it versus time, and you can perhaps get an optimum cleaning time. Or you just say, I need to clean here, and that's forget about it, instead of worrying about the optimum. The other thing you should recognize about the heat transfer here, it's as a diagnostic tool. When you were sick, your parents measured your temperature with a thermometer. Now, that was a diagnostic tool. In other words, they were using the heat release from your body to detect it by the rise in temperature as a way of determining whether you were sick or not. Chemical reactions. Chemical reactors very much dependent upon contacting and mixing. Right? Reactions must be brought together. Without contacting and mixing, there is no reaction. So your objective is to produce the desired product, maximize the product, minimize operating and recycle costs, minimize impurities and separation costs, and minimize safety and environmental concerns. All right. So you design for good liquid circulation, eliminate hot spots, cold spots, stagnant regions, minimize concentration fluctuations, hot spots, cold spots. I already said that. I guess I got it. You want to mix perhaps. You've been taught reaction engineering in your kinetics course, your reaction engineering course in college maybe. But in the real world, things are quite different. First off, in your college education, I suspect you primarily spent time on single-phase reactions. You also spent time on simple reactions. But when you have, say, A plus B going to R, right, you have this situation. It's going to R. Now, R is very valuable. R plus B again, right, gives you S, and S is a waste. Not only that, it's carcinogenic. So in such a situation, you want to cause this reaction to occur and prevent this reaction from occurring. So your reactor design, and that's what we're talking about, is to, again, maximize this reaction, minimize that reaction. One way of doing that is you have your stirred tank of A sitting here, and you drop in B. So B comes dropping in here like that. Little drops of B. So when B reacts with A to form R, there isn't any more B around to react to form S. What you probably want to do is not only feed B, but you want to feed B right into the vortices of the impeller, because that way it's a very high shear zone, and as a result, it would perhaps prevent this second reaction from taking place. That's one way of doing it. Another way would be if you run a static mixer here, and you have a side entrance of B coming in, okay? And then you have a little bit of the mixing going on, and you have A here coming in down the pipe, and then you flash it, or you freeze it, or you crystallize it, or you extract it, something that does the separation. In other words, you want to separate R away from B. And whatever you do to maximize the R and keep it away from the B is great. So oftentimes you want to mix, you want to react, you want to mix fast, react fast, and then also separate fast. In other words, oftentimes you want to hide the product. And the design approach for reactors, now you got to look at all these specialty chemicals that you can buy. Okay, I assure you, they were not all made in a stirred pot, right, or a plug flow reactor. They have all sorts of ways of contacting these specialty chemicals. They're not sharing. Yes, they're not sharing. They might for a price. Anyway, the design approach for chemical reactors should be: you look at the kinetics, see what you want to pick as what you want to emphasize, and decide what you want to prevent, and then design the reactor to do that, or at least attempt to do that. You do not want to force the kinetics, however complicated they are, into a fixed stirred pot. That's a stirred tank reactor, CSTR. That's not a very good way of thinking about it. We already mentioned that most chemical reactions are multi-phase. 25% of those is gas liquid. So the idea of getting the mass, usually it's oxygen, often it's oxygen, get the oxygen in quickly. You design the reactor as a contactor rather than, quote, the classic reactor that you've learned in university life. Simple test to determine if mixing effects are important. Mixing is unimportant, which, look at it this way. You have reaction time, okay? There's reaction time out there. And then you have mixing time. Now, if the reaction time is very, very long, it doesn't matter about mixing. Mixing is over with a long time ago. Mixing, remember, is easy. If you have a very slow reaction, right, then the mixing will have very little effect. However, if the reaction's fast, right, then you find out that the mixing time may equal the reactor time. As soon as the thing is mixed, it reacts. So that would mean that the mixing time and the reactor time are the same. So you have a whole slew of situations out there, whole gamut. This is often expressed as a Damn-Kohler number, the ratio of transport time to reaction time. But if you have the situation where mixing doesn't really matter, then the method of feed is unimportant, the feed location is unimportant, fluid properties are unimportant. However, if you have mixing causing the reaction, and the reaction time is equal to the mixing time, then all these, you do have effective method feeding, feed location, and fluid properties. Effects occur. When I was a young student in organic chemistry class, and being very much a skeptic on lots and lots of things, I kept on asking my organic chemistry professor, why did the reaction go that way? Why didn't it go this way? Why is this reaction the 100? He said all the reactions in this book go 100% the way it's. Now that guy just doesn't quite understand the reality of life here. If you take a whole bunch of soups, a soup of stuff, your reaction is going to be multi-leveled. I mean, there's going to be a lot of reactions taking place in there. Not just the single reaction that he was trying to teach me. Anyway. So, and again, this is a pretty obvious statement. Material in reactors often not homogeneous. Reaction, oh, I love this. The reaction volume is often not the volume of the reactor. I'm always amused by reaction rates. You have this rate equation, right, is equal to minus 1 over volume. That's a real problem right there. What volume is that? And then you have the dCA dt as the definition of reaction rate. I have several problems with this equation. I don't know what volume it is. And I don't know what concentration I should be using up here. If you remember the static mixer where you're mixing red and white, right? So there's a whole bunch of places that reactions can actually take place. So my favorite question whenever I deal with scale-up of reactors is reaction, where is the reaction? And I would very much advise you to videotape with a camera, right? You need your camera. You got to videotape what's ever happening over here in the lab so you know where the reaction was. So we wind up with a situation that reliable scale-up of a reaction needs knowledge about the reaction volume. Yeah, you know the reactor volume, but do you know the volume of the reaction? It always sort of bothered me on how they could get away with lying to you so easily in reaction engineering course. Reaction engineering course is not an easy course. Consider designing the reactor as a contacting device, perhaps a separator, perhaps a heat exchanger. Reactor is back-mixed or plug flow reactor is most often not an effective design. Again, I said this, most reactors are multi-phase and mixing issues need to be addressed. Sometimes you want to mix fast, react fast, and separate fast. Good starting point is assume all reactions are fast. If you assume all reactions are fast, you may catch intermediates that you have not identified, right? Reactor design requires an understanding of physical processes inside the reactor. Attention should be paid to how the various phases are interacting. Dead zones in reactors is yield loss, purity loss, production loss, but the biggie for the business people is profit loss. Profit loss. And of course, as I said earlier, you got to compare reaction time with mixing time. Reaction time is faster than mixing for most processing vessels. Some reactions are extremely fast and require fast mixing. Comparison of reaction and mixing times is necessary. Timescales for feeding should be compared to the reaction and mixing time. It takes a long time sometimes to feed something. Fast reaction geometries may require fast separation or quenching mechanism. So the equipment is not thought of as a reaction. Some reactions and equipment matches. The reactions are over as the material enters the equipment. Precipitation reactions are like that. Some material leaves the reactor before the reaction even takes place. An example of that would be car backfires. The gasoline comes into the engine. Maybe some of it burns, combusts. Some of it goes out the tailpipe and burns in the tailpipe, so you have a backfire. Add dropwise with good stirring is an indication of mixing effects, right? This is the A plus B going to R, and then the R going to plus B going to S. Local mixing determines local concentration. That's another thing back here. See, the problem with this reaction rate here is you spatially vary. It's varying with space. Variations all over the place in space. That's why you go to a microreactor or do study microreactions, is because there is no transport problems in these microreactors. Volume is so small that you do know the reaction volume. Again, videotape everything. Case in point, this one scale up, I think I've mentioned this earlier, but I'll do a repeat. Everything went well in the lab and went to full-scale production, and they did the first run in the plant, and all the material balled up on the impeller. Now, if they had ran video studies of the reaction in the lab, they would have known that happened. The plant people would have known that would have happened. And the comment was by the lab, well, we picked up the reactor and shook it, and as a result, the material came off. But you can't pick up a 10,000-gallon reactor and shake it to get the impeller off the shaft. An example of videotaping and how very important it is to find out what physically is going on. Starved systems, feed rates determine local concentration. You might say that a reaction is selected 94% of the time, 97% of the time. It's a little difference between 94 and 97. However, 94 has 6%, and this will be 3%. 3% undesired, 6%, that's a factor of 2 an unwanted product. Side reactions, they occur. Cause separation problems. Byproducts are less valuable, less desired, proper mixing minimizes side reactions. Changes in synthesis route may be helpful. Prevention of side reactions or quenching may be necessary. Side reactions cause a reduction in product. Side reactions. 5% reduction overall yield happens for a reason. You should find out why. Very expensive. For reactor design mistakes, you lack information, you lack understanding, you lack experience, you lack time. Some I'm laughing because I'm thinking about what I'm about to say. Some people, you have a heating coil in there, right? And the heating coil is pretty dense, and you feed right here between the coil and the wall. That's asking for problems, because that becomes a significant dead zone. Or this one here, the material, basically what happened is the material comes in here, flows across the top of the reactor, then leaves, and never participating in here. Or how about this one? The feed comes in, flows along the bottom, along the wall, and then out the bottom down here, exit. Because the reactor is filled with foam here, right? The whole reactor is filled up with foam, and there is no way of getting rid of the foam. So the material just bypasses the volume. So those are some of the standard problems that one might encounter. And if you don't believe this happens, well, there's hope. There may be some hope for you yet. Which brings up the point, if a reactor is performing poorly, you need to look at the mixing. Chemists, as far as I can tell, are really superior people, and the chemistry is well worked out. Maybe I should say, to the best of the ability of humankind to work out the kinetics, they usually have done a superior job. The mixing is the problem. Retrofits fit the product to the reactor. There you go. That's the first mistake, right? There is little or no opportunity for design. You have a standing tank there, use it. So you got a process that does not really want to be in a stirred tank, but there is a stirred tank, so use it. And the point of the matter is, retrofits can be made. Retrofits are common in industry. For example, you have in gas liquid systems, you had everybody using these flat blade impellers, and now they've turned to the Smith impeller. At least some people have. Not all, some. Where you have the curve. That would be a retrofit, right? Or if you have a fluid foil, if you have a pitch blade turbine for overall mixing, you replace it with a hydrofoil. A hydrofoil saves you a lot of money in pumping costs. So retrofits are common in industry. And changing the impeller is quite easy. It's not that hard, usually. It's amazing. You make a generalization and you're bound to be wrong. So I qualify all my generalizations by saying usually. Ling was the the director of research inside Dow. Described a process that required a high turbulence level to the desired product. Process had a critical fast reaction step. Turbulence levels occurred in small scale. Large scale, process failed. So, feed location was not identified. Right? Feed location was then identified. First, when it was failing, it was not identified. Lin comes in and changes feed location, and he walks out like a superstar, right? Changing feed location is a standard technique for improving reactor performance. Sort of like one of our major things that we do. So you go in, and the reactor is doing poorly because you're doing a surface feed. You come in and then change the feed location to the vortices if you can, and everything works out like a champ. Anyway, reaction, where is the reaction? That's why you want to videotape the lab studies. You want to make sure you figure out how fast the lab studies feed rate was coming in at. You want to see where the reaction occurred. It's not homogeneous. Let's see if we have a video here. Let's see if we have a video. I may or may not have this video. I apologize if I don't. I don't have that video. Anyway, the video is about the RC1 reaction calorimeter. Okay. And basically in the video they show a poorly mixed system and how they had a slurry reactor of some sort, and all the solids were at the tank bottom, and they were commenting that they were having a great, they were commenting that they were able to take great data that they could use in scale up. I seriously doubt that. Seriously doubt that. Some of the other situations that I've run across. Okay, let's go to options, color. Let's go to highlighter first. Then I want my color. What shall we go? Let's try blue. One reaction had the tank was shaped like this, and all the solid, liquid surface up here, and a couple impellers in there. All the solids were buried here, down in this exit pipe. And they couldn't figure out why the reactor wasn't performing. Catalysts were down here, unavailable for processing. The reaction essentially did not occur. So they did all kinds of things. They came in with a gas lance. They couldn't get down in the back. Couldn't get down in the pipe far enough with the gas lance to blow the gas. So eventually they did what we referred to as a back blow. Okay, so they blew gas up the pipe, and the catalyst took off. Was well suspended, and the reaction took off really fast, and scared the folks, scared the people. Anyway, let's go on and scale up and mixing. This is the old-fashioned way of doing scale up, and it's fine. It's worked well somewhat. Ways of which processes is similar. There's a lot of this stuff about geometric similarity. Well, what about kinematic similarity, dynamic similarity, thermal similarity, chemical similarity, all kinds of similarities out there. And the one that really kicks me, really gives me, they talk about incomplete similarity, and then they talk about complete similarity. Now, incomplete similarity, well, they're similar. They're already incomplete. They're not identical, so they're similar. So what they're saying is incomplete similarity, that's really strange. They use the word incomplete. And then the word completely similar, that's also a very odd thing. If they're completely similar, what does that actually mean? That's a very odd combination. Very odd. Anyway, this is what I seek. I always like to seek process similarity. It's so vague. I don't tell you what the process is. I talk about vague things like mechanism, same product, quality levels, geometric similarity and non-geometric similarity. By the way, you really, truly always want to try to do non-geometric similarity. You want to improve your process. You want to design the large scale. You do not necessarily want to do exact scale up. And you want to improve your process as you scale up. There you go. Remember the ratio of worker to the size of the job? You want that to be a larger number, large scale. See, way back when I said the worker divided by the size of the job should equal constant on scale up, that's true. And if that's not kept constant, if it goes negative on you, you have them walking around, you said, they'll say something like that, well, we could do it in the lab. I don't know why they couldn't do it in the plant. Whereas if you improve that ratio on scale up, you can walk around and say, well, we did a better job than the lab people did. Ooh, what fighting. Anyway, different levels, different types and levels of similarity. Same similarity, flow rates, complete mathematical and phenomenological identity. Wow. Same geometry, flow condition, energy levels, boundary condition. By the way, same geometry may actually prevent the rest. Scale mismatches, scale matching, and scale similarity. Scale matches must be made. Right. Equipment to process, process to process, and scaling, equipment to equipment and scaling. Processing mistakes, scale up mismatching can be used to advantage to identify mistakes. Examples of scale matching, examples of scale mismatching. Slow reactors in a fast mixer. Obviously, the reason why you would want to do that is, that's the second one down here that you want. To control fast reactions, you want to mix it slow. By the way, slow, slow, fast, fast, you're comparing mixing time with reaction time, right? These are slow reactions to a fast mixer, which means the mixing doesn't matter. And you have fast reactions in a slow mixer, that means the mixing controls, right? So scale mismatches identifies potential process failures. You usually also find that absolute mathematical equivalency is not scalable. The conditions required for the two processes to be mathematically equivalent is the requirements is really out of sight. Exact mathematical identity, here's the listing of those. We don't necessarily have to go through that. Okay, this hit geometric similarity one more time. It's the accepted norm. I hope not. Going forward, we need to get rid of this concept. Shape kept constant. Rarely done in practice. Exactly, that's true. Even though a lot of people aspire to geometric similarity, it's rarely done. It's not needed. Used for convenience. Reduces work. Here's the problem. Limits alternative designs. Now that's the real problem there. Limits good and perhaps better designs. Oh, yes. Guess I used the word better too many better times here. Geometric similarity can be used as a starting point. Yes, not required. Similarity handicaps good design. Why is geometric similarity so popular? Who knows? It's a poor concept. It's a really poor concept. Scale up becomes easier when the question of process similarity, process geometry is removed. There you go. If you keep the geometry the same, then the process geometry is something that you have to worry about has been removed. Scale processes may become impractical because of geometric similarity. This is true. More choices are available if geometric similarity requirement is removed. Anyway. Well, let's see what we got here. Successful scale up, you need to state the objectives, the controlling mechanism, the appropriate correlations and data, the appropriate geometry. From these will come the scaling procedures. Problem areas, there's no clearly defining controlling mechanism. There are several controlling mechanisms. The mechanisms change with scale. Those, oh boy, that's tough. Clearly defined controlling mechanism, know several controlling mechanisms, and change with scale. Anyway, I said this earlier, much earlier, you need to state stuff in English, or excuse me, in words, and then transfer them into equations. Elementary scale-up procedures require the identification of what does the mixing. We already got done saying you can mechanically mix, but there's also jet mixing, gas sparging, boiling sprays, natural convection. Obviously, you don't want to scale up on a non-dominant mixing mechanism. Right? For example, let me give you an example. I have one of those fantastic plastic straws. Just one. So I have my cup of water, my glass of water sitting here. But then I have a feed jet coming in. And that glass of water, the mixing in this glass of water will be controlled by that feed jet. This plastic straw will practically do nothing. Right? Power levels and geometry specify large scale. Geometry is specified by a scale factor. Here we go. This is the old-fashioned way. I don't particularly care for this way, but we need to talk about it. Just sort of give you a background of how useless it is. No, excuse me. I didn't mean to say the truth here. And no, it's not really useless, but actually it tells you what you can't do more than what you can do. First off, you got to look, you got the flow regime, process physics, it's turbulent. You also have the impeller controlled mixing. You have the controlling mechanism that does the mixing. And then you have geometry. So you have three biggies: flow regime, what's doing the mixing, and geometry. So if I go power per volume, okay, and I check into what power is and what volume is, I find out that it's n cubed d squared. Power is densities have been canceled. If scale 2, it's written as that. Now, you have a lot of people believing in power per volume, and I kind of believe in that too. It's a good concept. Basically, it's worker the size of the job type concept. There are some people that are out there, this is Lightning Corporation typically, but other people as well, industry. There are people who scale up on tip speed, and this is Chemoneer. And there's people that scale up on torque, which is, I think, the old Philadelphia mixers. They're all three the same. They'll have scale-up rules based upon torque. They'll have scale-up based upon power per volume, scale-up based upon rotational speed. But if power per volume, good concept, d cubed, see the d's to the fifth, so I get, there we have it. So when it comes right down to it, on scale-up, we have what size we're going to. So typically we have that ratio. We usually know what D2 is. And we know what N1 is. So then if we can figure out what N2 is, everything will be fine, because then we can specify power per volume for scale 2. Typically we know everything about scale 1 and what size we want to go to. So we really want to figure out what power per volume scale 2 is, and then we know the volume of scale 2. So we can calculate the motor size. So let's rush ahead here. Okay. We're looking for equal heat transfer per volume. And so equal, that's heat flow rate maybe. Volume is proportional to the heat transfer coefficient area divided by volume. The delta T's have been canceled out here, so to speak. The delta T is going to remain constant on scale up, so we just simply dropped it out. So we go to our heat transfer correlations. It reduces down to that. We substitute in for the Area is d squared, volume is d cubed sitting there. The heat transfer coefficient pops right in here by rearrangement of this equation. Okay. Or we quickly find out heating for volume is n to the 2/3 d to the minus 2/3. This is impeller now, mind you. This is not necessarily this is not heat transfer by steam injection. It's not heat transfer by boiling, or it's not heat transfer by injecting CO2. It's anyway, you go through correlations and you do some more algebra in there, and you quickly find out power per volume scale 1 to power per volume scale 2 is d1 to d2 to the 5th power. And basically it says that the scale up will fail, right? Unfortunately, the power per volume impracticality of trying to maintain equal heating per volume on scale up. You find out that d2 to d1, scaling factor of 2, you have power per volume going up by a factor of 32. In fact, the heating may actually be caused by the impeller action rather than the actual heating mechanism, whatever it was thought to be. So, geometric similar assumption is that this is geometrically similar. If we go a scale up of 10, things get even worse. So it's again more and more impractical. So you can add massive tank internals. You can inject live steam. You can inject, if you're cooling, you can inject, well, cooking requires heat input, but for processes that you want to control the temperature of, say like an exothermic reaction, you can't get the heat out fast enough. By the way, this is, if I reverse this, right, and look at it again, maybe it's also reaction rate, an exothermic reaction sitting in here, and instead of equal heat transfer per volume, you want to have heat controlled per volume, the heat release of the reactor. This gives you an idea that trying to control a large exothermic reaction on scale up using a geometrically similar process is going to be really dangerous. Really dangerous. You have an assignment if you have, there is a very famous accident, T2 Laboratories accident. I want you to go watch that, T2 Laboratories. And that's another comment about reaction engineering. Anyway, laboratories, I can't write here. Anyway. So if you do change geometry and you start doing area is proportional to the d cubed, this is possible, by the way. It seems very odd that area is a volume, but you can make area volume by, if you take a look, one of the techniques of doing heat transfer in pipes would be you fuse together metal spheres. And when you fuse together metal spheres, it makes a very good heat transfer. But if you assume that you're going to fill the entire reactor up with heat transfer surface, that's, by the way, sort of like injecting live steam. The injection of live steam would be a volume process because the jet of steam coming in is going to go through a volume and condense in a volume, I guess. And lo and behold, when you go through, that's possible. Anytime this exponent is less than 2, well, let's put it like this. When this exponent's low, less than 1, it's probably a good process. From 1 to 2, it's iffy. And 2, it's impossible. So that might be, you got iffy in here. Sorry, that's a technological, highly sophisticated engineering term called iffy. I've just invented the iffy number. It's a process that may actually be tough to accomplish. And down here we have the impossible stuff, like walking on water. Of course, this is impossible. Walking on water is possible if you freeze it. Again, it's just a matter of how you approach a problem. Which brings up my comment about engineers. The best way of solving a very difficult problem is to go around it. If you try to solve a difficult problem, a serious difficult problem, then you got to really analyze whether the problem really needs to be solved. Isn't there an alternative way? So scientists like to bang their heads up against the wall with this problem over and over and over again. I think engineers are more apt to just go around the problem. So the equation turns out to be much more practical. You're adding a deep area, significant area on scale up heat transfer area. Equal heat transfer coefficients. Well, on scale up, it may be important to processes that burn, coat, cake, freeze, etc. There's a number of things out there. Go to our heat transfer coefficient equation. Nusselt number is a function of Reynolds number, Prandtl number, and viscosity ratio. We may want a D over T ratio. Cancel out all fluid properties, lead constant, and voila, we have it being practical. Go through the equation. This is our objective on scale up. So we specify D1 we know power over volume 1. N2 is where we're scaling to, the size we want to scale up to, so we calculate P, power per volume scale 2, and then we specify the motor. So then we fill in the rest of the design with good geometry. Equal blend times, that's kind of interesting. N theta equal constant. That's not practical. Round 2 here, you get into the iffy factor here. Usually it's not possible to have the same mixing times on scale up if you're going diameter of 10, factor of 10 in diameter. And that isn't good. So equal blend times or equal mixing times on scale up is not possible. So usually you have to back away. I worked this problem earlier on when you changed to process objectives. Twist. Now, a real bad twist is right here. Mixing time correlations for ineffective mixing becomes exponential with volume. Right? So we have this exponential volume effect in here. So equal blend times on scale up are very difficult to obtain. I don't know if you remember that. Let's go back. Let's see, where was that? Long time ago. See, this is the, right there. This is mixing time, all right, as a function of tank volume, and it's this is a log scale. This is linear. So it says that basically this slope in here. By the way, these data, just a quick glance at this data. These data are an average of 10 each, right? 10 each. And up here, this condition here, I have no clue why that happened. But most of the data fell along the lines. Anyway, let's go back. You can scale up from something that's reasonably mixed to something that doesn't mix at all. There you go. That's the major difficulty. That would be a terrible situation. So you're going to watch the T2 laboratory problem. I mean, the very famous accident. They made a huge number of mistakes. First off, They relied on city water for their cooling. They had a reactor that had a cooling system in there, and they relied on city water for their cooling. That was it. They didn't have a backup. I mean, you can throw stones at them. All kinds of mistakes that they had made. So we quickly find out that you can't mix large scale, small scale the same way. In particular, again, if you're scaling up and you're going from a reasonably mixed system to an ineffective system, then you certainly are going to fail. There's my slide. Sorry. Equal bubble and drop diameter. Now, I showed you the videotape on the static mixer, the drops being broken up. Now, that's basically a function of the Weber number, and this is where this is coming from. Now, you got to recognize exactly what is in this correlation, and not much. Not much. This is drop size dependent upon the Weber number type of thing. It's for very dilute systems, and it has no effects of surface charge in it, no countering effects due to coalescence. There's a whole bunch of stuff that's left out of this correlation. But we find out that equal power per volume, scale 1 equals equal, that's what it says, equal power per volume on scale up. Equal power per volume 1, scale 1, equals equal power per volume, scale 2. And if you look at that, it sort of makes sense. Basically, you have a drop, and you stretch an interface. The amount of energy required to stretch that interface is the same, whether you're small scale or large scale. So as I said, it's very dilute, simple systems, effects of coalescence, high drop concentrations, non-Newtonian effects, electrical charge effects are certainly not apparent in that correlation. By the way, this is an awful simple correlation, and most engineering correlations are very simple, right? They don't really have very much going for them. No, all seriousness. Okay, correlation suspect. Correlation and scalp information are suspect when these effects occur. Nature can be very complex, and a simple correlation is not able to model the phenomena. Yeah, correlation is for low volume fractions, low viscosities. That's also true. If you go viscous, the correlation may or may not hold. Equal mass transfer coefficients. This is a real problem here. Equal mass transfer coefficients for bubbles and drops. Okay. And suppose you wanted to have that, equal mass transfer coefficients on scale up. If you go here, classic boil down, so to speak, of mass transfer coefficient, KLA, gas power, this is gas from the gas power of the impeller, and this is superficial gas velocity or sparging. And if you take a look at this is a power source, the impeller is a power source, and this is a power source as well, gas sparging, all right? So gas power input, superficial gas velocity. What's interesting, these exponents are not constant, okay? The range of variables of these quantities also can be quite dramatic. So down in here we have the superficial gas velocity controlling. The power per volume is not doing very much. Up here you have the power per volume controlling. Okay. And over here you have nothing. Basically it goes flat again. And this is probably what might be referred to as a choked regime, as I said earlier. So we have two major power sources here, trying to determine the outcome. A and B vary. Right? So you got a real mess on your hands, basically. And scale-up procedure becomes difficult since A and B change. A and B are complex relative magnitude. So you got a real terrible situation. Don't believe it. Oh yeah, there are equations, and there's an equal sign, but don't use. It's not great. So what the devil do you use? Well, you build the best system you can. You want this is a bottom line backup approach to scale up. You build in a lot of options to your equipment. You're looking for nimbleness. You're looking for flexibility. You're looking for robustness. You're looking for easy cleaning. You're looking for effective geometry. So you go with those approach. You buy superior, to your knowledge, superior equipment. All right. You go and to the rumor mill and see what the rumors are. You go to companies that have a similar process but are not competitors. The food people can talk to the pharmaceutical people and find out what's being used there. And that would be most helpful. Getting back here, most fermenters that you see in a lab often have the distal impeller at the bottom, and then a pumping hydrofoil there and another hydrofoil there, and the wall baffles. Now this is classic fermenter. It may not be as classic anymore. But as opposed to that design, I would go in with 3 Smiths, Smith, and Smith. Sparge to all 3, and see what happens. I have another design actually for the gas liquid contacting, but I'll keep that to myself in case somebody's interested. I'll talk to you about it. However, it was done for a major pharmaceutical company, and as a result, I'm sort of hesitant about talking about it. But it was intriguing. It was, you study something, and then bam, right out of the blue, something hits you. And that's, that's kind of the way things happen. Anyway, equal Froude number. Froude number is important. Surface. So you're talking about equal solid suspension. That would be possibly Froude number, modified Froude number, as we saw earlier, or that would be, and modified Froude number on scale up is possible, right? So equal solid suspension, that's very similar to equal Froude number, right? And we already talked about the modified Froude number. And this exponent is 85.7 and 0.6, so that's possible. So research in solid suspension, however, has to be described as confused. Have you ever heard of research being confused? Well, it's sort of like the way it is with solid suspension. And it's for a good reason. Solids are a very difficult phase. I mean, solids themselves are very variable, right? Solids are very variable, right? And their surface behavior is variable. There's sort of like 7 different surface chemistries, and then you have this thing of agglomeration that can happen, and then the fact that the surfaces aren't pure gives you rise to the fact that you're going to have problems with suspension of solids, or I should say it this way, you may have unforeseen problems on scale up of solids. Now then, we have an interesting change. We're going from turbulent, and look at that title. Flow regime, laminar. Mixing controlled, geometrically similar. Okay, we're going to assume geometric similarity. I don't know why we're assuming geometric similarity. It makes people feel good, I guess. But quickly we find out that power per volume scale 1, power per volume scale 2 is N is equal to this. Viscosity, rotational speed squared, scale 1. Viscosity, rotational speed scale squared, scale 2. And if we cancel out viscosity and cancel out the diameters here for power and volume, we quickly find out that power per volume scale 1 to power per volume scale 2 is N1 to N2 squared, so to speak. So if we specify the ratio N1 and N2, we assume the viscosities remain the same. If not, you can include that variation if you wish. Anyway, we go do a rough design, figure out what M1 and N2 should be. And quickly we go through equal heat transfer for volume, and it's even worse than we thought. Power per volume scale 1 to power per volume scale 2 is 1/8 power. That's totally impossible. You're not going to be able to accomplish that. Remember, if it got above 2, it became impossible. If it's between 1 and 2, it's iffy. So what happens? An exponent of 8 is very high. Significant ramifications. A factor of 2. It gives you 256 times more power. Power is usually prohibitive and simply not done. Actually, what happens is the scale-ups go very small. Not 1 to 10, but 1 to 1.5, 1 to 2 maybe. Laminar applications where there's such a requirement, chemical reactions go usually very small. Okay, this usually means laminar equipment has small diameters. Internal heat is broken, then we'll still come up with a very difficult task. The objective is still mostly impossible. Okay. Equal heat transfer. Right. For laminar systems, it's again a square, and that becomes difficult. Scrape wall surfaces should be considered. Right. Now, what happens is if you had scale 1 just being a regular pot, and then you scaling up to a system with a scraped wall, this is a scraped wall, a scraper, things could drastically could be improved. If you have a pot on the stove, take a look at this, comment on geometry. You have 2 pots on the stove, and you're stirring this pot with a spoon. There's only one little contact point down here where you scrape the bottom of the pan. However, if you come in with a spatula, right, you have a huge contact area. So if I am cooking pudding on the stove, I don't really want to use a spoon. I want to use a surface scraping paddle, so to speak, to keep the pudding from staying on the surface, which, by the way, is an assignment I want you to do. To understand heat transfer and laminar flow conditions, I want you to cook pudding on the stove. I think I gave this assignment to you earlier. So you add the powder. You got to add the powder to the milk, and now you're stirring. And the powder goes into the milk without any lumps, which is great. And you stir and stir, and it's fine. It's turbulent. You have no problem. So you walk away. Okay, that's a mistake, because eventually the pudding is cooking, and then the starch molecules are going to swell up, and the viscosity goes from 1 to 1,000 to 10,000. And now you're no longer in the turbulent regime. You are now in the laminar regime. Turbulent to laminar transition. Your heat transfer problems go up enormously, and so you have to go with a scraped You turn down the heat, is what you do, so it doesn't burn, and then you go with a scraper, a spatula, rather than just the tip of a spoon. Equal blend times. What's amazing about this is possible, believe it or not. Right. N1 to N2, equal mixing times were not possible, turbulent flow. Here they seem to be possible laminar. Kind of interesting. What happens is mixing in laminar flow is stretching interfaces. And to stretch an interface requires energy. And it's saying to stretch an interface, it's the same laminar as well as turbulent. Ineffective mixing geometries. Mixing can't be accomplished on scale-up. No scale-up procedure prevents this. One perhaps had effective mixing on the small scale. Effective mixing on the small scale. Now has ineffective mixing on the large scale. Ineffective mixing large scale may not be recognized. Much time and effort are wasted trying to figure out why there's such a difference between the two processes. Well, it's just they're different processes. So procedures outlined above can be applied to equal brought by or equal, can be applied. Other items. Solid suspension in laminar mixing, not particularly difficult. Density differences are not important. Once suspended, the solids will remain suspended, and the bottom scraper is recommended. You have a chunk of amber, and in that amber is an air bubble. It's been in there for 1 million years. And the density difference between the amber and the bubble is quite large. But it doesn't matter. Gravity's not working very well. Very important point about laminar mixing. Jets are not effective. Remember the video I showed you where you have by G.I. Taylor? The jet comes in and piles up. Right. No mixing. As opposed to a turbulent jet that spreads out really everywhere, right? So jet mixing is not effective in laminar flow situations. Surprise, surprise. Changes things. So what you have is you have stuff that is practical and stuff that's impractical. So some scale-up results are practical and some are not. Again, the exponent is greater than 2. Impractical scale-up procedures include equal cooking, both laminar and turbulent, equal blend time turbulent, equal heat transfer coefficient laminar mixing. So let's draw a conclusion here. And scale-up is open-ended and not a clear-cut process. A lot of uncertainties occur due to poorly defined process objectives, poorly understood process mechanisms, and how they change with scale. And the biggie is the lack of information is most harmful. Most harmful. Anyway. Scaling research. And at this point, I'm going to take a break for a second or two, and maybe I'll come back. I'm going to come back. Anyway. Let's proceed to talk about scaling research. Now, very few people do scaling research. They study scale-up of a process. As a result, they're doing some research into scale-up. But very few people are actually studying scaling. Well, you call it process translation. Translation is designing a larger unit. Not necessary to have the exact process or equipment. Exact scale-up is certainly not required. Certainly not required. You want to design the larger scale unit. Pilot plant studies should attempt to duplicate the plant. The laboratory studies should duplicate the pilot plant. Proper plant objectives. Those are the objectives. A proper plant operation is the objective. And people get very angry when I tell them successful laboratory and pilot plant studies come and go, but a successful plant makes profit. So process translation is the design process of taking small to large. For mass production, large cash flow, creation of wealth. And you should also be studying the economic impacts of your variables. Scale down and scale up, or processing at different scales. Difficult tasks should not be considered lightly. Model studies are very, very important. Processes obey the laws of physics and chemistry and biology. They do exactly what they're supposed to do. And they change as a function of size. And scaling and process translation should rely heavily on pilot plant studies. The trend is away from pilot plant studies, development of engineering, basic understanding, computational ability, and theoretical knowledge. And so you see that some companies do very little piloting. Piloting is not needed when the company stays with the same technology. And pilot plant studies can be ignored if you have good process experience and available engineering knowledge. So, if you have a company where the new products are being developed all the time, some companies have 50% of the products conceived in the last 20 years, then you find out that scale-up process translation studies are needed. New products remains very important. Extensive piloting studies are done. Process translation, very risky if piloting is not done. If it's limited, very risky if experience and engineering knowledge is not present. Pilot plant studies are needed for new products, new processes, new processing techniques. However's, processes are constantly changing. New variations of products. Processes are never established exactly. Requires technical decisions and compromises. It's sort of like hitting a moving target. And process objectives are always changing. So we have a situation where some technologies are from the 1950s, 1940s. These should be examined. New plants should be built to their age. 2020 plants should be built on 2020 technology. New techniques are needed to remain competitive. Failure rate. 1 out of 100 makes it, right? So the failure rate's interesting. Many processes are stopped in the piloting stage due to improper scale-up. If done properly, success would be a lot higher. Information here. Select the plant design. It's technically okay. Equipment will perform expected. Pitfalls, procedures are examined. Retrofits, very common. Processes fit. Fixed processes are the exception. New technology is being developed. And you have environmental safety regulations always changing. Good pilot plant studies require thought and expertise. They just don't happen. Reviews are needed and should be appreciated. So you have the negatives of piloting and you have the positives of piloting. Time is required, negatives. Let's talk about negatives. Time is required, revenues not being made. This is the biggie. Even imperfect plants make money. Markets are being lost. Market advantage erodes with time. Easy systems don't need pilot plant studies. Positives, if you're going to correct mistakes in the plant, it's going to be expensive. You potentially have difficult startups. If you don't do piloting, 5-year startups, not. There was a famous startup of a company in Jamaica. Basically, everything had to be redesigned. Costly to study on a commercial scale. Scaling mistakes are often costly. Scaling studies lead to higher efficiencies, lower capital investment, easier process startups. So you have the positives and you have the negatives, and I recommend doing both. You rush to market, so to speak. That's the term, rush to market. And at the same time, you do piloting studies. So that's what I would do. Time value revenue lost or balanced by losses due to poor piloting. Prior experience is useful. Process optimums justify piloting. Environmental safety issues also justify piloting. Right. Cost of pilot plants is insignificant. Best not to conserve costs. Don't restrict capability. Cost savings in piloting is nothing. Cost savings, the loss of versatility can be very high. Pilot plants should have a full range of capabilities. So I got kind of, we have scaling objectives, testing suggestions, testing concerns. They overlap each other. Processing plants the ultimate objective. There's a hierarchy. Objectives need to be addressed. Not all are going to be satisfied. Not all are going to be satisfied. So the general question is, what is occurring? How differences occur? Why differences occur? Many, many questions. What do you want to do? Why? Why do you want to study? Why? What information is needed? Why? Right? Objectives. General scaling objectives is to answer a lot about what you want. All kinds of questions. What's desired? What's the information? How's the information going to be used? What level should be scaled to? Scaling tests should be well established and help direct findings. Knowledge comes from experience. Experience is gained in piloting. Experience provided by successes and failures. Scale up ratio, well, you can go from the lab to the mini plant. Some people are production facilities, the mini plant. Then you could possibly go to the pilot plant, semi-works, and the plant. So those are some of the names for a gradual succession of pilot plants. You don't need, you can go from the lab to pilot plant to plant if you like. Definition of the problem. What's the objectives? Objectives of the process form the basis for the scale up, by the way. Forms the basis for the design. It's an ongoing process. It's not one time and done. Not one time and done. You do it over and over and over again. Right? If you do it one time and think you're finished, you're probably not done it right. Again, we already said this. Lack of information, lack of understanding about scaling. Studies should fill these gaps, right? We already said that. Have a working process, at the right scale, expect the production rate, plan rate, cost, quality, and cost restraints. Process definition, lots and lots of questions. This is process characterized, fed, kinetic rate, mass transfer phases, problem phases. So processing problems come from a lack of information. Perform process explore, operating conditions, limited information. What's doing the work? What is doing the work? No reason to scale up on a mechanical agitator if the dominant mixing mechanism is a jet or a pump. Boiling, free convection mixing, calculation of various times needed. Experimental time. You got to figure out what's happening in the time. Recognize the effect of mixing mechanisms. Mechanism identification. Mixing has competing mechanisms. Heterogeneity causes different environments. Each may contribute in different ways. Impossible ideas. Expectations. No matter how hard I try, I cannot fly. Okay? very impossible for human beings to fly by themselves. Okay, so there's a whole bunch of stuff out there that's not technically possible, does not come to fruition. You want to find these early. Not all systems are scalable. Not all systems are scalable. I was asked by a company, basically they were using super glue and to seal cuts, wounds on your finger. And they wanted to add pigment to the super glue so that when it sealed the wound, it looked the same color as the. First, it wouldn't be shiny, and second, it sealed the wound the same color as the person's skin. And this is essentially a non-scalable process because what happens is the pigment, being a powder with air in it, caused the super glue to really react rather fast, too fast for you to seal the cut. So not all processes are scalable. Only scalable processes, right? Non-scalable process comes to you from a very famous chemical company. They had a design. They spent 2 years on this, design a suitable product, design a process. The catalyst for the process was not suitable. They knew this. The catalyst that was being used had a process life of 2 weeks. So they spent 2 years to scale up this process. And to be profitable, the catalyst had to have a life of 1 year. So they spent $70 million. And the process scale-up was stopped. The process never developed. The reason why it was never developed is they couldn't find a catalyst that had a life of 1 year. They knew this was impossible going in, and that was the conclusion coming back out. Catalyst life was not available. 1 year catalyst life was not available. So people knew the catalyst restriction was impossible to overcome when they went into the process. So anyway, $70 million spent, a whole bunch of people in designing this process, and it couldn't be built because the catalyst life was a week. Anyway, expect disagreement between data and theory. Knowledge is very limited. Scale-up studies reduce or eliminate uncertainties. Some unit operations are predictable. Some unit operations are not predictable. Right. It's very important to recognize that. Distillation, for the most part, is predictable. You can throw it on a computer. Aspen can calculate the distillation process. However, other processes tend to be not very predictable at all. Filtration, mixing are notorious. We said crystallization process and precipitation reactions are somewhat unpredictable. You can't throw these types of processes on Aspen. So one distinguishing feature between predictable and unpredictable processes is whether Aspen can be used in the calculations or whether it cannot be used. And after you have the Aspen calculations of whether they make sense or not. So, here's an interesting question for you. If you have the general correlation, here's the general correlation. And for individual processes, do they agree with the general correlation? And here they do. However, here's another process. And basically you see divergences going on from what the general correlation predicts and what individual systems do. Whether I have a picture of that or not, I'm not sure. This dash I had. We're dashing really much further ahead here. Sorry. This is what I'm talking about here. This is an example that basically you have that data trend like that, data trend like this, data trend like that, and data trend like that. You can see that the correlations, you can do this with all the data available. You can see that individual processes or individual data do not necessarily agree with the overall correlation. That's a real serious issue. So, to be quite honest with you, this is more prevalent than this. Okay. What in truth of the matter is the general correlation represents a cloud of points. It represents a cloud of points, not a single line. And you can have variations, all kinds of things in that cloud. And not necessarily this at all. This is probably does not occur very often. Anyway, it's a matter of debate. So the scaling objective would be to gain process experience. Scaling studies performed to establish operating correlations, flow regimes, confirm effects, proper geometry and energy levels. Finding the controlling mechanism. 1. Some processes are difficult. There could be several controlling mechanisms. Pilot plant information could be very valuable. Again, the idea of gas power from the impeller and gas sparging power gives you an example of several controlling mechanisms. Process performance. What are your performance indices? Have these been characterized in a rational manner? Requires definition and procedures, perhaps. Equipment selection. Acceptable changes from standard geometries are tested. Again, process-specific geometry, Smith impeller, hydrofoil, helical ribbon. Rapid equipment comparisons are possible. Equipment efficiencies are different. Efficiency impacts upon equipment selection. Optimum points are very much needed. Recognizing the problem and the process is important. Developing scale-up procedures are important. How to troubleshoot. How to model, process operability and procedures, reproducible results, development of measurement procedures, analyzing data, process sensitivities, determining scale effects. Here you go. You measure gas down here, and there isn't any gas. You measure gas up here in the gas band, there's 50% gas, and up here it's 15% gas because bubble call. Here you have a slurry pipeline. You take a measurement of solids content down here, and you quickly find that you should shut down the pipeline because it's filled with solids. Up here, there is no solids, so you have no problem. Process heterogeneity exists everywhere, and they significantly affect process measurements. You really, this may seem very odd to you, but you want to make mistakes, right? Gave a talk one time about making mistakes, and the guy got up after me and said, "You don't really want to do that." Anyway, when somebody tells you you want to make mistakes, well, you're on a learning curve. You want to... What's really tricky is when the mistake is not a mistake at all, but quite a revealing, could have quite revealing information. Anyway, cost of mistakes in the pilot plant is low. Cost of mistakes in converter plant is very high. Make the big mistakes in the pilot plant. Don't make the big mistakes in the plant. Learn from your mistakes. Idiot-proof your process. Some comments about mistakes. Christopher Columbus sailed in 3 ships, not 1. And it's quite obvious that he figured that 3 ships, at least 2 of them sank, he'd still make it. I don't know what he would do if all 3 of them sank. The number of successes don't really matter that much. One failure will shut you down. So you really, really want to idiot-proof your process. One mistake will shut you down. So you always want to consider mishaps and process failures. Now, what you call process failure is kind of interesting as well. When you add powder to a stirred vessel and you create lumps, and then you spend 12 hours dissolving away those lumps, is that a process mistake? Well, it certainly isn't optimum, that's for sure. So, think of it this way. You're in a room, and there's this hose, and you got to step over this hose back and forth all day. And it's really a very aggravating experience until you move the hose. Get the hose out of the way, and then you don't have to worry about it. I've seen that happen. A person just tolerated the bad situation, just tolerating a bad situation, had an easy solution. Took them a long time to get around to doing the easy solutions. Process uncertainties occur, failure studies, boundaries. Many properties operate at or near failure boundaries. And this is where the best efficiencies occur. Define and understand your flow regimes. Develop scaling objectives. Also, this is interesting. When Pellington studies are often done to discover processes of your competitor. Identify problem regimes. Extreme and processing properties lead to difficulties. Find these. Adequate seals for environmental safety issues. Processes change with time. Change with size, but also change with time. Scaling studies, scoping, feasibility, 1 and 2 point investigations, proof of principle, optimization, confirmation of information, all kinds of things. Now, I strongly endorse optimum sloppiness. Small, quick studies to accomplish verifications. I also like flow visualization. Flow visualization, videotape of lab experiments is excellent. Of course, I like computational fluid dynamics. I don't do it, but other people do. So I would enjoy some of that. You should take a look at some of that. And side-by-side comparisons are always kind of unique if you can accomplish that. But let's go to optimum sloppiness again. I always was impressed with this report, mixing efficiencies of static mixers. This is, let's explain what the y-axis is. This is a mixing index. The lower this number is, the more mixed it becomes. And this is length to diameter ratio of the static mixer. The length of the static mixer to its diameter. And you can see this SMX has 2 data points, right there and right there. And so it begins with a mixing deviation of 3. There's a reason for that because it goes up and down like that. That's deviation here, 3 to 1. So it starts out at 3. And quickly you see that this one drops off real quick. I'm not sure about the details of this experiment, but I would suspect he had a flow loop. He could jam in a static mixer, take 2 data points, pull it out. Jam in another static mixer, take 2 data points, pull it out. Same thing here, same thing down here. So he was doing a 2 experiment. Actually, he only needed to do 1. Anyway, with 2 data points, he established the lines for each of these static mixers, right? He did not go into a detailed, this was an experimental program, I think. And he did not fill in the data points, right? If you notice. He just took 2 data points. He didn't do a saturation run on this, right? Right. I have, I always, thermodynamics, people in thermodynamics doing research, they love to have the data line. They love to have the theory line, and then they fill it in with data. So that's the biggest waste of time. Holy tamale, am I going to get in trouble for that one? Up here we have PMR. I'm not quite sure what PMR is, but certainly they're not doing so hot. And down here I suspect that I have an in-between. Again, optimum sloppiness. You throw in a static mixer, take 2 data points, pull it out. Throw in another static mixer, take 2 data points, pull it out. Here's this one here. Can't hardly read that. Anyway, so you have mixing index or mixing measure performance. This is performance index versus L over D. Now, you would have to assume that SMX is the best mixer. Okay. So this is what I mean by you can make rapid equipment comparisons. Okay. Excellent, in my opinion. Now, having said that, I also got to throw darts at it because I got to tell both sides of the story, right? I suspect the SMX is putting in more power per volume. There's much more power going in, doing a lot more work than the PMR. I suspect the PMR people or the lightning people, it takes an awful long length to eventually get down to 0.01. But, you know, the lightning static mixer may not be using this, certainly not using the same amount of power per volume as the SMX. So the point of the matter is you can make rapid equipment comparisons. See, what they should also do is show you pressure drop, what the pressure drop was. Because pressure drop times volumetric flow rate is power, right? So you should plot performance index divided by power. What was the power input and what was the mixing? And then you would probably get a better idea of what static mixer is more efficient than another. So, you know. But I really like this study because you can make rapid equipment comparisons. You can eliminate static mixers that apparently are not working very well, as opposed to those who have high power input and are working very well. And that's my idea of optimum sloppiness. The concept of optimum sloppiness is that you don't want to study a mediocre or lousy process, or you don't want to study a mediocre or lousy geometry, right? You want to be selective on your geometry. So, I like 1 and 2 point experimentation. Process is forced into other geometries. See, that's the problem. You got stuck with one piece of equipment. The process is forced into that one piece of equipment. The other equipment has not been investigated. The geometry is the most important variable, and you're not studying it. Limited equipment is not good for scale-up. 1 point experimentation is for the constant. Often you got some dimensionless groups, equal sign, and you have a process result. Between the two is this constant here, and you need to determine what that is. So determine the constant and the correlation. That constant may cancel out on scale up, but you should investigate what the constant is anyway. Testing by vendors is possible, or tollers. That's a good idea. Full-scale testing on existing equipment is certainly recommended. If you got the right size, there is no scaling involved. You will also find that the large scale tends to be inflexible and limited range. That's why you have a laboratory, is because it provides a lot more flexibility than the plant. Now then, scaling difficulty. Scaling is easy when the process is repeated. You also find single-phase gas liquid easy to scale up. More difficult are heterogeneous systems. Excuse me, let me say it this way. Scaling is more difficult in heterogeneous systems. Different phase combinations causes difficulties. Processing vary depending upon size. Different flow regimes occur. And size-dependent process impose problems. Scale-up differences are caused by different surface volume ratios between the two scales. Scaling of an unmixed, non-homogeneous system is always going to be difficult. There you go. Some systems do not scale. Process phenomena do not happen on a large scale. Laboratory personnel should be given guidance as to what data and information is necessary. Plant engineer, I'm going to get in trouble for this one. Plant engineers should select the laboratory equipment. Get out of here. Anyway, much more so than they are doing now. This should probably be stated more politically correct manner and say plant engineers should select some of the laboratory equipment. Equipment selection should be for easy scale up. Why make it hard on yourself? You already got a hard enough problem as it is. Experiments should be performed in scalable systems. Communication, very important between the pilot plant and the lab. Everybody talking to each other. In other words, the lab should be inside the plant, and the pilot plant facility should be right beside the lab. Everybody forced to talk to each other. That's why lunchtime is so important. You sit around and talk about shop all day, and then, you turn around and talk about shop all the time and then eating lunch. Equipment used in experimentation should resemble actual plant equipment. That's a good idea. Heating and cooling is often critical. You need to have flexibility, be able to change the heat transfer. The T2 laboratory problem, right? They should have several backup systems to prevent the accident that they had. Instead of relying on the city water for cooling, they should have had that plus an emergency shutdown. So, with another completely different approach. Anyway, taking a good sample, I mentioned this earlier, basically cross the moving stream entirely, watch that sample. Laboratory personnel may not recognize how to carry for a sample. Handicap is isokinetic sampling. Sampling techniques are not isokinetic. Techniques aren't developed. Difficulty performing the plant. Distillation column, dead of winter in Pittsburgh, Pennsylvania. They wanted the vapor stream, the top tray. So they went in and had a tap up there, and they collected it up in a beaker. 20 degrees Fahrenheit, gale winds, this material froze in the tube. Never got to the beaker, collection beaker. So as an example, whether you may have thought you got a sample, but you really didn't. Anyway, I'm going to stop there. Pitfalls and analogies. We'll begin at another time. Anyway, thank you very much.